Hello, everyone, and welcome to this week's session of the Bitcoin Optech newsletter. And today we'll be covering newsletter number 287, published on 31st of January 2024. And as every week, we'll commence with the news section. I'll go through the preface of what today's newsletter comprises of. This week's newsletter describes a proposal to allow replacement of V3 transactions using RBF rules to ease the transition to cluster mempool, and summarizes an argument against Optech template verify based on it commonly requiring exogenous fees. Also included are our regular sections summarizing top questions and answers from the Bitcoin Stack Exchange, announcing new releases and release candidates, and describing notable changes to popular Bitcoin infrastructure projects. So the first article is titled "Kindred Replaced by Fee," and it is based on a post by Gloria Zhao. So Gloria Zhao posted to Delving Bitcoin about allowing a transaction to replace a related transaction in the mempool even if there's no conflict between the two transactions. Two transactions are considered to be conflicting when they cannot both exist in the same valid blockchain, usually because they both try to spend the same UTXO, violating the rule against double spending. The rules for RBF compare a transaction in the mempool against a newly received transaction that conflicts with it. Zhao suggests an idealized way to think about a conflicts policy. If a relay node has two transactions but can only accept one, it should not choose the one that arrives first. It should choose the one that best suits the node operator's goal, such as maximizing miner revenue without allowing effectively free relay. The RBF rules attempt to do that for conflicts. Zhao in a post extends the idea to related transactions rather than just conflicts. Bitcoin Core places policy limits on the number and size of related transactions that are concurrently allowed in the mempool. This mitigates several loss attacks, but means that it might reject transaction B because it previously received related transaction A, which maxed out the limits. This violates Zhao's principle. Instead, a Bitcoin Core should accept whichever of A or B is actually best for its goal. The proposed rules for V3 transaction relay only allow an unconfirmed V3 parent to have a single child transaction in the mempool. Because neither transaction can have either ancestors or dependents in the mempool, applying the existing RBF rules to replacements of a V3 child is easy, and Zhao has implemented it. If, as described in last week's newsletter, existing LN commitment transactions using anchor outputs are automatically enrolled in the V3 policy, this would ensure that either party can always fee bump the commitment transaction. And these are the four permutations. Alice can send the commitment transaction with a child transaction to pay fees. Alice can later RBF or existing child transaction to increase the fees. Bob can use kindred replacement to evict Alice's child by sending a child of his own that pays higher fees. Alice can later use kindred replacement on Bob's child by sending a child of hers with an even higher fee, removing Bob's child.
What's kindered replacement?
Yeah, we'll go through that. I'll just read through the text, okay, just a couple of passages, and then we'll go through it. Adding this policy and automatically applying it to current LN anchors will allow the CPFP carve-out rule to be removed, which is necessary for cluster mempool to be implemented, which should allow making replacements of all kinds more incentive compatible in the future. As of this writing, there were no objections to the idea on the forum. One notable question was about whether this eliminated the need for ephemeral anchors, but the author of that proposal, Gregory Sanders, replied, I have no plans on dropping ephemeral anchor work. Zero Satoshi outputs have a number of important use cases outside of LN. Coming to your question, sort of what are kindred replaced by fee? Broadly, it's a proposal that allows a Bitcoin transaction to replace another sibling Bitcoin transaction by fee. Up till now, the replace by fee mechanism that we have in Bitcoin is applicable only to conflicting transactions, meaning one transaction can only replace another transaction by fee as long as they are conflicting with each other, meaning both the transactions are trying to spend the same input. So if there are two transactions that are relayed, both are trying to spend the same input, then the one that pays the maximum fee will be mined, and the one that pays the lesser fee will be ignored. Okay, but the condition or the prerequisite here is that both the transactions should necessarily spend the same input, and thus they are referred to as conflicting transactions because both those transactions can't be embedded on the blockchain. Only one of them can. What's kindred replaced by fee? This is a proposal by Gloria Zhao where she proposes that replaced by fee should not only be confined to conflicting transactions. Even if two transactions are spending completely different outputs and they are not conflicting with each other, still there should be a mechanism to replace one by the other through which the miners are incentivized. Okay. Now, a broader example that she gives to prove her point is for instance, like in recent weeks, we've covered that an unconfirmed transaction in a mempool cannot have more than 24 unconfirmed ancestors or 24 unconfirmed descendants. All right. Now let's assume there's an unconfirmed transaction in the mempool which has 24 unconfirmed descendants. All right. So now the limit is up. It cannot have any more descendants. All right. Now let's say somebody broadcasts another descendant. All right. The 26th descendant in the list, including the transaction itself. And this transaction, this 26th descendant pays a very huge fee. Now, despite the fact that this 26th transaction pays a very huge fee, let's assume this 26th transaction pays more fee than all the 25 preceding transactions. Despite that, the miner will not be able to include it in a block because it violates the mempool policies, which is a shame as far as the miner is concerned because he loses out on the fee. Now, this mechanism in itself, restricting the number of descendants, is important to prevent DOS attacks. However, from a miner's point of view, I mean, it's something demoralizing for him because the limit has been reached, so he has no option but to choose those 25 existing transactions, even though they do not pay a high fee. So people basically, you must have heard in the previous sections, we talk about cluster mempools. Now, people who are advocating for cluster mempools, they suggest that we get rid of these ancestor and descendant limits. Currently, the limits are 24 ancestors or 24 descendants, including the transaction itself. If that limit is reached, you cannot have any more ancestors or descendants which are unconfirmed, or it's I think 1000 k virtual bytes. Okay, so if a transaction has unconfirmed ancestors or descendants that reach this weight, then it cannot have any other unconfirmed ancestors or descendants. So people who are advocating for cluster mempool, here you can see, you can read in detail further if you want later, cluster mempool. They have come up with a mechanism where they believe that this hierarchy of ancestors and descendants should be, it should be warded off, it should be abandoned. Rather, all unconfirmed transactions that are related to each other, they should be considered as one cluster, no matter what their number is. Okay, so we need to get rid of this number limitation. We need to consider all the transactions that are unconfirmed and related to each other. They should be considered as one cluster, a cluster of transactions. Then we will split that cluster into small chunks. Okay, and now the transactions will be included in a block depending upon which chunk has the highest fee. So we get rid of the 24 descendant and ancestor rule. We get rid of the size limit. Okay, we just take into consideration all the transactions that are available that are related to each other. We see, I mean, we integrate all of them and we split them into small clusters. Okay, and the cluster that is paying the highest fee should be included into the mempool. This is what their proposal is. Okay, now how this kindred replaced by fee works is that, for instance, there is a commitment transaction in the Lightning Network. Okay. Now, this commitment transaction, in the previous weeks, we studied that commitment transactions have anchor outputs. The only reason for which is bumping fee. Because every time you update the status of a Lightning channel and you create a new commitment transaction, you have no idea when you're going to spend that commitment transaction. And that is why it's not possible for you to stipulate an exact and precise estimated fee. So generally what's done is that the channel partners stipulate a very low fee so that they can bump it at the time of broadcasting it. And for that, they use anchor outputs, which are zero transaction value and zero fee outputs. And the only purpose of those anchor outputs being there is that they can be used as a fee bumping mechanism, meaning you can attach a child to that anchor and that child will have a good fee. And that is how you can get your commitment transaction broadcasted. Now, what Gloria Zhao suggests is that there are two anchor outputs in every commitment transaction. Okay, one for each channel partner. If there's Alice and Bob, Alice has one anchor output and Bob has one anchor output. Okay, so now if let's say Alice attaches a child to her anchor output in order to broadcast the commitment transaction, okay, and Bob also attaches a child to his anchor output having a fee greater than that of Alice's, then Alice's Bob's anchor output or Bob's child transaction for that anchor output should be able to replace Alice's child transaction for that anchor output. Okay. Now these are completely different transactions. Okay. They're not spending the same output. Alice's anchor output is different. Bob's anchor output is different. Alice's child is different. Bob's child is different. They are non-conflicting transactions. The only thing common between them is hierarchy. They're at the same hierarchy. Okay. So there's the funding transaction, which is at the top, which is the parent transaction. Below the funding transaction, there's the anchor output, which is an unconfirmed transaction. And below that, there is the child transaction. Okay. So the only thing common between Alice's child transaction and Bob's child transaction is that they are at the same hierarchy. So broadly, what Gloria Zhao proposes is that even if two transactions are not conflicting with each other, even if they are not spending the same output, if they are at the same hierarchical level, then the minors should be be lured or intrigued into choosing the transaction that has a higher fee and neglecting the transaction that has a lower fee. So this is kindred replaced by fee. Okay, it's taken from the word kin, which is a family, or they also called it as sibling eviction or cousin eviction. So these two transactions are basically siblings or cousins or from the same kin because they are at the same hierarchical level. And the example that she gives is that Alice can send the commitment transaction with a child transaction to pay fee. Alice can later RBF her existing child transaction to increase the fee. Okay. Then Bob can use kindred replacement to evict Alice's child. Okay. So now Alice has attached a child to her anchor output. Bob decides to attach a child to his anchor output with a fee higher than that of Alice's. So now Alice's child transaction gets replaced by Bob's child transaction, even though they are not conflicting to each other. And Alice can later use kindred replacement on Bob's child by sending a child of her with an even high fee. So now let's say Alice wants to replace Bob's transaction. Yeah.
What? How is it being replaced? So what happens to that transaction, which Alice's transaction replaces Bob's transaction? So is it just moved out of the mempool? I don't quite understand what replacement means in this context.
It's invalid because it's trying to spend the same input that the Bob is trying to spend because it basically gets replaced. I think you have a very valid question because in contemporary RBF, what happens is that the transaction that replaces the earlier transaction, okay, it is spending from the same input. Okay, so when it's spending from the same input, the transaction that is replaced gets invalid. Okay, because the inputs that it is referring to do not exist anymore. They have been spent by another transaction. Okay, but here because the inputs are different, right? Alice's anchor output is different and Bob's anchor output is different. So if Bob's child replaces Alice's child, what happens to Alice's uh, anchor output? I mean, one situation could be that it gets mined. This article does not cover it. One situation could be that it gets mined because it's a zero value and a zero transaction fee output. So it might either get mined. That's the only logical solution because the anchor outputs are not getting replaced now. The anchor outputs are not getting replaced. Only the childs are getting replaced. Okay. So the Alice's anchor output is still there. Alice's anchor output is not getting replaced. Bob's child is replacing Alice's child. Okay. So Alice's anchor output is still there. It's only Alice's child that will not get spent.
Okay. Okay. Yeah. So another question is like mempool policy is not part of consensus, right? Because it's client specific and mempool policy can be anything depending on whatever implementation one is using.
Right. As from my understanding, that's 100% the case. Node policies and mempool policies are not consensus policies. And we'll cover that in this week itself. What are the parameters that determine what's a consensus policy and what's not a consensus policy? Only the parameters of Bitcoin that are backed by hash rate can be included as consensus policies. Parameters that can be varied by different mempools or different nodes cannot be consensus policies because it basically is a mempool operator that determines what their policies are. So to the best of my understanding, it's not a consensus policy. If anybody would like to contradict me with knowledge, please go ahead and do so. But my inference is that node policies and mempool policies are not consensus policies.
Thanks, Faisal.
They are not consensus.
Yeah, great. Okay, so yeah, any observations, any questions regarding what are V3 transaction relay, what are anchor outputs? We've covered them, but still if any. Yeah, sure.
Yeah, I had a question. So because because in kindered replacement the transactions are not conflicting, so like how is it replacing the other transaction? Like they both could exist at the same time.
Yes, they both could exist at the same time, but I mean, it's like there these are treated. I mean, the way the article is worded, these look to be treated as two different versions. One version of the transaction that is trying to spend it using Alice's child, and one version of the transaction, the same transaction that is trying to spend it with Bob's child. And the miner obviously will give preference to the version that is trying to sell it, spend it
Yeah,
with
you
the
know what?
higher
I
fee.
got it. So yeah, in V3, I just remember that in V3 transaction you can have like only one child. So it's
Right,
replacing that child. So they
right.
can't be two. So two transactions can't exist at the same time. Correct? Yeah. Thanks.
No, but I personally feel that that might not be the reason because see, Alice's child is for Alice's anchor output, which is specific to Alice, right? And Bob's child is for Bob's anchor output, which is specific to Bob. So, like these
But
two children
they
are not, yeah,
yeah, but they both have the same parent transaction. So one V3 parent cannot have two child transaction. So the Bob's transaction, which has a higher fee, will replace Alice's child.
by parent, do you refer to the funding transaction or the anchor output?
The transaction that creates that anchor output.
That is not their, yeah, but that is not their parent, right? The anchor output is their parent. The funding transaction is the parent of the anchor output, and the child transaction's parent is the anchor output itself. So these
So
are two different anchor
funding
outputs.
transaction has the like they're the same transaction. So funding transaction is the one that creates those anchor outputs.
Yeah, but they are two different anchor outputs. And one more thing to add to the V3 policy is that the policy says that one unconfirmed transaction cannot have more than one unconfirmed child. As far as the funding transaction is concerned, it's already confirmed. So it does not comply with the V3 policy at all. It's only the anchor outputs that need to comply with the V3 policies because the anchor outputs are not confirmed. The funding transaction is already confirmed. So I feel that might not be the reason. The only reason that I would infer is that there are two child that are trying to spend the same commitment transaction, and now the miner has the authority or the prerogative to choose one, and if miner chooses one, the other gets replaced by this one.
I'm pretty sure that's not the case.
Okay, yeah, maybe that's my inference. That might be wrong, but I mean, I don't think VP transaction has anything to do with it as well. But we can take it up later. No issue.
Yeah, we can,
All right.
we can.
Yeah.
Faisal, you just a clarification. You said that they're spending the same input. Is it the anchor output are two different inputs, right? Because they are recorded separately for Alice
Yeah,
and Bob.
they are trying to spend the same commitment transaction, and anchor output is a part of the commitment transaction.
Right,
Anchor
but
output
anchor
is one
output
of the
being
outputs of the
different.
commitment transaction.
Right. But them being different makes it separate transaction, right? So if there are two anchor
No, they
outputs,
are different outputs of the same commitment transaction. I mean, one parent transaction can have multiple outputs, right?
right,
And
right,
it's anchor outputs are basically locks on a transaction. Until and unless you don't spend an anchor output, you cannot spend the transaction.
Hmm.
Okay, so if the
Yes.
anchor output is spent, then the other outputs of the commitment transaction are spent. Basically, in a commitment transaction which has multiple outputs, it's only the anchor output that can be immediately mined. All the other outputs have a CSV of one block. So it's the anchor output that is mined that unlocks the commitment transaction, and after one block of which it is the other outputs of the commitment transaction that are mined.
Right. Makes sense. Yes. Thanks.
But I mean, like these are like very new proposals. So yeah, there's a lot to discuss and lot of permutations and combinations. I mean, there can be a lot of different ways of understanding the same text and a lot of possibilities because they're still being explored. These are ideas, these are brain children of developers that are being exposed. We don't have like a concrete documentation to go through it and infer that this is the only output or this is the only version. These are just being discussed right now in the community. So
So the
they might
status
have
quo is
multiple
it's just
possibilities.
right.
It's just
Certain.
is Gloria Zhao's brainchild. That is it.
Yeah, it's only a proposal for now. Is it?
Yes, exactly. Yes.
Got it.
Now the next one is opposition to CTV based on formally requiring exogenous fees. Peter Todd posted to the Bitcoin Dev mailing list an adaptation of his argument against exogenous fees. See newsletter number 284. Applied to the Optech template verified proposal. He notes that in many, if not most, CTV use cases intended to allow multiple parties to share a single UTXO, it is difficult to impossible to allow for sufficient CTV variance to cover all possible fee rates. It is expected that CTV would be usually used with anchor outputs to pay fees, or possibly via transaction sponsor software. This requirement for all users to have a UTXO to pay fees negates the efficiency of CTV using UTXO sharing schemes. The only realistic alternative is to use a third party to pay for the UTXO, example via a LN payment. But at this point, it would be more efficient to pay an out-of-band mining fee. That, of course, is highly undesirable from a mining centralization perspective. Links added by Optech. He recommends abandoning CTV and working instead on covenant schemes that are compatible with RPS. John Law replied that fee-dependent time locks, see newsletter number 283, could make CTV safe to use with endogenous fees in cases where particular versions of a transaction needed to be confirmed by deadline, although fee-dependent time locks might delay some contract settlements by an indefinite amount of time. So last week I think it was last week when he spoke in detail about exogenous fees and endogenous fees and out-of-band mining fee. And we also talked about CTV and what role they play in governance. All right. So this basically is Peter Todd's opposition. He is not in favor of CTV, and he feels that other mechanisms should be explored, which are compatible with RBF to implement Covenant, because CTV is not RBF compatible in its current version. And the opposition that he shares is broadly, it has to do with, again, OpCTV leading towards minor centralization by inducing out of band mining fee. Now, how does that happen? OpCTV has like multiple use cases that are being proposed. In fact, if you go on social media, the people that are advocating for OpCTV, the number of use cases that they mention, you feel that this opcode has a solution to every problem in the world. Okay, so they claim that this they claim that this OpCTV will facilitate or ensure transaction aggregation, which is multiple people can share the same UTXO. Up till now, we have public key aggregation and digital signature aggregation, right? In P2TR transactions, when like in case of a taproot, you have this concept of internal key where you aggregate multiple keys using, for instance, music. And we also had a session with Saravanan on music, in which he covered public key aggregation and digital signature aggregation. So basically, you can take multiple public keys and aggregate them to make an aggregated public key. So instead of using those individual keys to sign a transaction, what you can do is you can aggregate those keys and use that as what you would call a master key or an aggregated key. And same for digital signatures. Instead of multiple people digitally signing a contract on Bitcoin, you can aggregate digital signatures and turn them into one signature. Now, what OpCTV proposes is transaction aggregation, where multiple people can share a single UTXO. Like, for instance, if an example could be if there's an exchange that wants to disperse funds to its customers, then it can, instead of individually giving those funds to each customer, if the customers agree, then they can give a shared UTXO to all the participants, and there can be many use cases. So broadly, it proposes shared UTXOs where multiple people can own one UTXO. Now, what this happens is, like just now we've covered commitment transaction. Commitment transaction is nothing but a shared UTXO. It's a shared UTXO between Alice and Bob. Alice and Bob together own it. Okay. Now there are two ways to take this, or three ways, in fact, to take this transaction to the main net. One of which is like mutually two parties agree and spend it, or one of the three mechanisms is somebody wants to unilaterally spend it. And if somebody wants to unilaterally spend it, in case of commitment transactions or in case of shared UTXOs, what happens is people generally negotiate on a very low fee because they plan to spend it in the future. Okay, and when they want to spend it in the future, if there's a fee spike, then they probably use a mechanism like an anchor output, like in commitment transaction. So what Peter Todd proposes is, or claims, is that OpCTV enabled shared UTXOs. You know, when multiple people, hundreds or even thousands of people, they claim can share a UTXO. When somebody from among those people wants to unilaterally go on chain, they will have to pay a high fee. And when they have to pay a high fee, they will need to have an anchor output. And if you have an anchor output, the drawback with anchor output is that you always need to have a child in reserve, right? Because the anchor output basically does not have any fee, does not have any transaction value. So you need to attach a child to it. Okay, now to attach a child to it, you always need to have a UTXO in reserve. If you don't have a UTXO in reserve, that anchor output is of absolutely no use. So when hundreds and thousands of people are you owning a UTXO in unison, and one person or a few people want to go to the main net, they will have to compensate for whatever is the surplus fee, for which they always need to have an anchor output, which reduces the efficiency of CTV. Because if you're using CTV enabled shared UTXOs, then you always need to keep one UTXO in spare, which you cannot use for bumping the fee of that shared UTXO to go on mainnet. And what this would do is that, what if you don't have a UTXO, right? What if I have a what if I have a shared transaction? I want to go to mainnet. I don't have a spare UTXO. All my fundings are in that UTXO. I don't have any more Bitcoin to use as a child transaction to bump the fee. What do I do now? So in that situation, people will have to resort to out of band mining fee. They will have to get in touch with miners and pay them outside the network, which again leads to miner decentralization. And how that leads to miner decentralization, we've covered in the preceding weeks. Because you can't even RBF a CTV, right? Because the CTV already has an address stipulated to it. And all the conditions are already mentioned in the template, right? It's check, template, verify. The template is already there. The inputs are locked, the outputs are locked, the address to which it will go is locked, the fee is locked, everything is locked. All right. So there's no point in furnishing a template and locking all the details when you have the authority to eventually change it. So you can't RBF a CTV transaction. Okay. So the only option for somebody who wants to opt out is to pay out of band a mining fee, and that is why Peter Todd opposes it, and he claims that there should be other implementations that enable covenant schemes that are compatible with RBF and not OpCTV. So this is like his inference that OpCTV shared UTXOs in OpCTV will lead to exogenous outer band fees, and thus we need to drop it and consider alternatives. And then John Law replied that fee-dependent time locks could make CTV safe. We've also covered fee-dependent time locks. Briefly, what's a fee-dependent time lock? It's basically a time lock where the time is only considered when the fee of the network is below your stipulated fee. Okay, so now let's say me, Bob, and Alice have a channel open, okay, and they have a commitment transaction, and both of them have agreed that this commitment transaction will only be spent for a fee less than 10 sats for virtual bytes, all right, and they put a time log of 100 blocks. Only those 100 blocks will be taken into consideration when where the fee average fee was equal or less to 10 virtual sat 10 sats for virtual bytes. So if 200 blocks have been mined, and all those 200 blocks had an average fee of higher than what Alice and Bob have stipulated, the HTLC will still count as 0 blocks passed. Okay, so only those blocks which are equal to or below the fee that Alice and Bob are willing to pay to go on the mainnet, only those blocks will be taken into consideration. So that is fee dependent time lock. The time only passes when the fee is less or equal to the fee that has been stipulated in a jointly owned UTXO. So this could be another alternative. This is what John Law replied. This is broadly the gist of the suggestion, what OpCTV is and how it can lead to out-of-band mining fee in shared UTXOs, how Peter Todd opposes it, and how John Law came up with an alternative suggestion. So that is what was covered. These are the only 2 news articles. So anything anybody has to share or ask before we move on to the next sections about CTV or anything?
So I have very general question. This is not related to CTV. My question was right now in the mempool, what is the oldest transaction which has still not gone through? Probably because the transaction fees was so low.
I mean, I don't exactly know. I don't think anybody can tell you what the exact transaction is, but there is a limit. I am pretty sure that a transaction cannot lie in a mempool for eternity. Firstly, there's a limit. Okay, I mean, there's a fee limit from my understanding. If your transaction is below that fee limit, okay, the nodes will not even relay your transaction. Okay, and if it's equal to or above that fee limit, and yet no miner is willing to include it, and it's languishing in the mempool for a lot of time, there is an upper bound. I'm pretty sure about it. There is an upper bound after which that transaction will be removed from the mempool. If anybody would want to
The reason I'm asking
add
this
on to
question
it.
is all these schemes of child paying for parent and then we talked about kindered payments. As in, the broad hypothesis therein is like a lot of times transactions will happen wherein there is not sufficient fees. Uh, is that like such is that really such an important edge case is what I'm meaning to ask. Like, is that a really such important case in the past, or is that something that's going to be the norm because of new kinds of op codes coming in, wherein probably a lot of people will be interested, or new kind of transactions wherein a lot of transactions will happen with very low transaction fees. Like, what is the reason that so much of research and so many newsletters are coming on these related spaces, these related concepts, RBF? Yeah, any
True,
idea?
that's a great observation, Setu. Uh, Firstly, as far as this concept is concerned, then I think it's pretty old because we've already had RBF, right? RBF was the first time, as per my understanding, was the first time where we tried replacing a transaction with a higher fee. So this issue has persisted. It's not a novel issue. Then we also have CPFP, child paying for parent. So these two conditions have already been there. Now we have V3 relay policies, which also enable you to fee bump a child and prevent you from paying a tax. There is this concept of CPFP carve out, where again fee bumping is done without paying a tax. So, firstly, this thing has always existed, and secondly, I mean, uh, in shared duty exos, generally what happens is that, like for instance, let's talk about CTV or about Lightning, right? In CTV or Lightning, what happens is that the conditions on which a transaction will be spent are predefined, right? When two people set up a Lightning channel, right, it is at that time. It is at that time that they decide what fee will they pay to go on the mainnet whenever they go on the mainnet. So when Alice and Bob start a Lightning channel, Alice and Bob decide that, hey, we're willing to pay X amount of fee to go on the mainnet. Now they might not go on the mainnet for 6 months, 1 year, 5 years, 10 years. You never know. They might never want to close their Lightning channel. They might close their Lightning channel after 6 months, 1 year, 2 year, 5 year. You never know. And at that, it's impossible for Alice and Bob to guess what will be the fee at that point in time, right? So generally, what they do is instead of coming across a situation where they end up overpaying, they keep the fee very nominal. So whenever there's a shared UTXO, the thumb rule that most people observe is that they keep a very low fee. Because if the fee is very low, you can bump it later, right? When you want to spend it. But if the fee is very high, there's nothing you can do to reduce that fee. So the more logical way of going about it is to keep a very low fee, and then when you spend it, bump it so that you don't end up wasting money. That is the mechanism. And generally, whether it's CTA, CTV enabled shared UTXOs, or whether it's a commitment transaction, the thumb rule is that people who jointly own a transaction and they predefine the fee that they are willing to pay for that transaction is generally very low. And when that happens, then you're in a situation where you cannot take that transaction to the main net except with bumping the fee. And that is why so much emphasis is given on this. And I think Peter Todd mentions in his post, if you go through this post, he says, I mean, it's Bitcoin's ethic and ethos that whenever a person wants to part out of a contract, he should be able to do that, right? If two people are in a Lightning channel, if one person wants to opt out, there should be a provision for him to opt out. It's his prerogative. You cannot tie him into a contract or a transaction without his will. And for that, there need to be fee bumping mechanisms, right? If there is no fee bumping mechanism, then you can hold that person into that contract against his will because there's no fee bumping mechanism. So that is why fee bumping mechanism is so important because it gives you the prerogative and the authority to opt out of a transaction or shared UTXO, for instance, if you don't want to be a part of it anymore. That's my understanding of it.
Got it. I think even in those cases, like paying minors separately by directly contacting them, though it will lead to exogenous. There are problems with the exogenous fees payments, but my I think just that is super simple, and I'm sure like such a service will come up in the absence of these elaborate schemes around CPFP, RBF, and kindred payments.
True, and I
Yeah,
think
and we
lastly,
want
yeah, sure.
yeah, and we want to avoid such kind of things because it affects it affects everyone because they won't have the knowledge of what's the current fee rate if out of band fees become a thing. So we want to discourage like fee payments like that.
But is all this extra additional complexity, including OpCTV, worth it to avoid that?
Not so like let's go over why we need policies like shared UTXOs and these complex RBF things. So block space is scarce,
Yeah.
and as the adoption grows, we'll see more and more people joining the network, running their node, and making transactions. So what these new proposals do is that they minimize the on-chain footprint. So instead of by shared UTXO, you can just have one UTXO that is shared between 4 and 5 people, and instead of having 5 UTXOs. So that is less burden for the network, using less block space, and then like everyone is happy. And the reason why we need complex schemes like RPF and V3 transactions is to like reduce the load on the mempool. So right now there are a lot of transactions in the mempool, and like almost half of the mempool, like it's almost double the usual mempool policy, which is like 300 megabytes. Right now it's around like 600 megabytes. And right now we are not even close to global adoption. So yeah, that's why we need these kind of things like V3 transaction that only allow one child to exist and then replace it.
Okay. No. So I think what you're saying is there will be more innovations like these in the times to come.
Yes, and we definitely need these.
Okay.
Another tidbit is that out-of-band miner payment is apparently not distributed among all the hashers by the mining pool.
Yes.
Oh,
So like
that's
it
a
will
trivia.
lead to minor centralization.
Who pockets it? Out of band keys.
The
Who
pool
pockets
operator,
it?
the pool operator apparently during the spam attack that happened recently, they have been adding out-of-band transaction with low fees, and they've been adding it, into the block without the transaction entering the mempool.
All right. So the solo miners are not aware of it. The pool operators are pocketing the fee, and the solo miners are made to believe that these are transactions with genuine low fee.
Yeah.
All right. Got it. Stack exchange questions. We'll just go through them as quickly as possible. How does block synchronization work in Bitcoin Core today? Peter Wool describes the block header tree, block data, and active chain tip block chain data structures, and goes on to explain the header synchronization, and block activation processes that act upon them. So this was a question asked about how does the block synchronization happen? Like when a node when you start running a Bitcoin node, how does it gain access, because it does not have any data, it's an empty node, right? So it needs to contact its peers and gain the relevant information. What is the current active tip? How does that process happen? So this is probably the most elaborate answer or article, whatever you want to call it, available on the internet. Okay, by Peter Wool. So anybody who wants to read it can go ahead and read the entire process in very detail. It's obviously outside the purview of our session. It's very long. Okay, he explains each and everything in detail. It's like a wonderful article. Whoever wants to read it. Broadly, he summarizes this process into 3 steps. Header synchronization. This is the first step, where the block requests only the headers, where the node requests only the headers from its peers. Okay, it requests for 2,000 new headers from every peer. So first, it gets access to the heads using the get header. It sends the get header message to its peers. The peers send 2,000 headers to it using the header message, and then it sends another message, and another 2,000 headers come, and then it sends another message, and another 2,000 headers come, like that. So that's the first thing, the header synchronization. And the block synchronization, once it has the headers, then asks for the blocks corresponding to those headers, and then those blocks come. And then finally, the third is block activation. This is where the checking is done, whether they're syntactically correct, and whether they're complying with all the consensus rules. And the block with the highest proof of work is included, and the chain with the highest proof of work is included 24, which is the active chain tip. So these are the 3 steps that are broadly involved in synchronization of the blockchain for a new header. Article is very good for whoever has time and interest in reading. But yeah, broadly it's divided into header synchronization, block synchronization, and block activation. 3 steps. The next question is, how does headers first prevent disk fill attack? So basically, what happens is just now we covered that the first step is that the node requests its peers to give it headers. Now this is done twice. Twice the node requests the peers for headers. Why is it? For the first time, the node only asks for the headers and checks if the headers have adequate proof of work. All right, because there is a pre-confined minimum amount of work that a header needs to have in order for it to be considered valid. It's possible that somebody might go back to the Genesis block, for instance, where uh, and execute a soft fork, because back then the mining difficulty was very nominal. So it's possible for somebody to go back to the Genesis block and from there cause a soft fork, all right, and then send headers of that fork to you. So there is a mechanism to detect that if somebody is sending a wrong chain, that the blocks that you are getting must have a minimum amount of, the blocks that are coming from a chain, the chain should have a minimum predefined amount of work for it to be considered valid. So the first thing the node does is that it asks for all the headers and verifies if the headers have a minimum proof of work that makes them eligible and legitimate and ensures that false headers are not being sent. Once that happens, for the second time, again, it sends the get header message, and this time it downloads this header and adds it to its database. So this is what headers first does. The first request of headers, which is only used to verify that the headers have adequate proof of work. How does it help and how does it benefit? It benefits you such that a false soft fork chain is not created and you're not fed wrong headers. The answer again is pretty detailed. We would like to go into the depth of it. And is BIP 324 transport redundant on Tor and I2P connections? Is Statusfer with us? Yes, she is. So BIP 324, as Statusfer has explained on various occasions, it's broadly a BIP that encrypts the data that is being shared between the participants on the network to prevent man-in-the-middle attacks. Now it does exactly what Tor does or I2P does, right? Tor also encrypts the data, and I2P also encrypts the data. So if somebody is already running a Bitcoin node over a Tor network or an I2P network, what added advantage do they have? What incentive do they have to switch to V2? Because the data is already encrypted. So why do they need V2? So P2 will basically say that as far as encryption is concerned, then there is no added advantage. V2 does exactly what Tor does or I2P does. So somebody who's using Tor or I2P, there's no added incentive as far as encryption is concerned to move to V2. But there's one benefit, which is that the data that is transmitted over in among the peers that comply with V2 transport policies, it like the byte stream that is transferred is less in size. All right, so the data that is transferred through a node that is V2 compatible is lesser in size. So there is less usage of bandwidth and there is less latency as compared to Tor and I2P. So the data transfer is quicker than Tor and I2P, but as far as encryption is concerned, then V2 does exactly what Tor or I2P do. What's a rule of thumb for setting the maximum number of connections? Peter Wool distinguishes between outbound and inbound connections and lists considerations around setting higher max connection values. So this question is regarding, is there an upper bound or a lower bound for inbound and outbound connections? Now, without specifying a number, Peter Wool, I think, is the one who's answered. Yeah, it's him. What he's basically mentioned the pros and cons between having less connections and more connections. All right. What he says is that you have more connections, inbound and outbound connections. There are less chances of you falling to an Eclipse attack, because the more the number of nodes that you are connected to, the higher is the possibility of you being connected to at least one honest node, and that will prevent you from falling for eclipse and partition attacks or partition resistance. So this is an advantage of being connected to multiple nodes or more nodes. And there are a few drawbacks as well. Bandwidth, because the more nodes that you are connected with, the more data you have to share. Every transaction you have to gossip with so many nodes. So it uses a lot of bandwidth. And a lot of bandwidth again leads to block propagation latency, because you're communicating with so many nodes and you're sharing every transaction information, gossiping on the network at every node. The block propagation will be delayed. Memory usage, you use more memory in your node, and obviously CPU usage. So there are four drawbacks of having lots and lots of inbound and outbound connections, and a benefit. So you need to weigh the pros and cons before deciding how many inbound and outbound connections you want to have. One thing I noticed while going through this answer is that I think a couple of weeks ago in one of our session, I think it was in our PR review session where we were discussing whether you have a control over inbound connections, whether a node can decide who can establish an inbound connection with it or no. What this answer says is that it does not have any authority. As long as the inbound connection is valid, the inbound connection will be established. I think Mango was there in that session. Shian was also there in that session. We spent around 5 minutes discussing this. So this answer, if you all can go through it, it says that you don't have a control. If the inbound connection is malicious or invalid, then it will be rejected. But as long as it's a valid inbound connection, it will connect your node. As long as it does not surpass the upper bound limit of inbound nodes. All right. Next one is why isn't the upper bound plus 2R on the block timestamp set as a consensus rule? We discussed what is MTP, median time passed, and we discussed what is NAT, network adjusted time, a couple of sessions ago. The question is, I think, referring to what you just asked a while ago, Mango. Why is it not a consensus rule? Why are the mempool policies not a consensus rule? Broadly, Peter Wooler answers that consensus, this is the gist. Consensus rules can only depend on information that is committed to by block hashes. So only that information which is backed by proof of work, which is backed by the hash rate, is has to be compliant to consensus rules. And your timestamp does not depend on the hash rate. I mean, it's basically time. Even when the hash rate is high, 1 second is 1 second, and even when the hash rate is low, 1 second is 1 second. So it does not go up or down, unlike your difficulty, which goes up and down. The number of blocks you mine, or the number of time elapsed between blocks, it varies in accordance with your hash rate. But block timestamp is independent to the hash rate, and that is why it is not a part of the consensus rule. It is a part of the node policy.
Yeah, actually, it's there in the word itself, I guess, consensus, right? It's on what we agree upon. I can keep whatever bullshit I want in my mempool, I believe.
Right, exactly. Same with your node. You can keep whatever time you want. It's just that other nodes will not interact with you, but it's your prerogative. You can keep whatever time you want. 2 hours ahead, 5 hours ahead, 10 hours ahead. Sigop count and its influence on transaction selection. User Cosmic Debris asks how the limit on signature check operations, SIGOPs, impact a miner's block template construction and mempool-based key estimation. User Mononaut outlines the infrequency of SIGOPs being the limiting factor in block template construction and discusses the bytes per SIGOP option. Uh, Broadly, what this question asks is the SIGOP count. Okay, like just like a block has a limit to which it can go, right? Like a block has a limit. A block can have only X amount of size, right? If you try to add transactions that supersede that upper bound, the block will not accept it. Likewise, the block has a Sigop count as well. Okay, the transactions that you are included in a block can only have certain amount of signature operations. All right, so those transactions have scripts. In scripts, they have signature operations, object sig or object sig verify, and there can be multi-scripts where multiple signatures might be needed. So there is, because these signature operations are data intensive, there is a limit to which the signature SIGOP counts can be included, meaning a block cannot have transactions that have more than a certain amount of signature opcodes in them. And if that SIGOP count limit is reached and it cannot accept any more transactions that have signatures, it can accept transactions that don't have signatures, that basically are paying to, for instance, opt to script. So the question is the SIGOP count also taken into influence or consideration when including a transaction into a block, so that, if a transaction has a lot of signature operations, you put it out of the block so that you don't reach the limit and you include another transactions. Does that play an influence? Uh, my understanding of the answer was that firstly, this user Mononaut pointed out that this happens very rarely. I think he mentioned 62 of the past 1,000 blocks had reached the SIGOP count. So this is a very rare occurrence, and there is no mechanism that can filter transactions based upon the number of signatures they have in them. Once you reach an upper bound, you just reach an upper bound, and then you either leave the rest of the block empty, or you include transactions if they're available in the mempool without any signatures. That is what it is about. There's just one release and release candidate. That's HWI, which is Hardware Wallet Interface of Bitcoin Core. That's what HWI stands for. Is the release of the next version of this package, providing a common interface to multiple different hardware signing devices The new release adds support for Trezor Safe 3 and contains several minor improvements. So the new release 2.4.0 of hardware wallet interface of Bitcoin Core has added support to Trezor Safe 3. It's a hardware wallet. Notable code and documentation changes. Bitcoin Core PR number 29291 adds a test that will fail if a transaction executing an Optech sequence verify opcode appears to have a negative version number. This test, if it had been run by alternative consensus implementations, would have caught the consensus failure bug mentioned in last week's newsletter. So, in mastering Bitcoin, we've covered what OpCSV and OpCLTV are. Okay, OpCSV is basically an opcode that allows time locks on transaction, and this is a relative time lock. Okay, OpCLTV is an absolute time lock. OpCSV is a relative time lock. Now, what happens is that these two opcodes are only compatible with Bitcoin transactions that have a version number of 2 or greater. Okay, so basically what Bitcoin Core does is that it checks what the version number is. If it's 0 or 1, it's not compatible with CSV or CLTV. If it's 2 or greater, it's compatible with CSV and CLTV. Now it adds another check to check if the version number is negative. It's negative, okay, because there are some other implementations of Bitcoin Core where even if the version number is negative, they are CSV and CLTV compliant. Okay, so they basically just check if it's 0 or if it's 1, then it's not compatible with CSV or CLTV. If anything other than that, it is compatible. And they were using signed integers. So even if somebody puts a negative transaction version number, the transaction will go through. It will comply with CSV and CLTV in certain other implementations like BTCD. But Bitcoin Core will reject it. So different implementations of Bitcoin will behave differently if a transaction has CSV and it has a negative version number. But now Bitcoin Core has added a test in which it tests, and even BTCD, whether the transaction, whether the version number is negative or no. So if it's negative, it rejects. If it's 0, it rejects. If it's 1, it rejects. If it's 2 or greater than 2, only then OpCSV and OpCLTV will get executed. Otherwise, it will not. Eclair number such and such add the ability for trampoline payment to use blinded paths for ultimate receiver. Right. So basically, what this is that Eclair is an implementation of Lightning Network. It's a wallet. Okay. So basically, what it has done is that it has added ability for trampoline payment. What's a trampoline payment? Like just like Bitcoin has heavy clients or full nodes and lightweight clients, right? Even Lightning has full nodes and lightweight clients. So let's say there's a lightweight Lightning client which does not have the topology of the entire network. In that situation, what that lightweight client can do is that it can find another node that has all the information pertaining channels and public keys of the different nodes on the channel and delegate it with the task of routing its payment, right? So let's say I'm running a node that is lightweight node. I don't have information about all the channels in the network. I don't have information about the public keys of all the announced nodes, but I want to send payment to a certain person. Now I cannot find the path because I don't have the relevant information to find the path. So what I will do is I will get in touch with a full node, just like you do in Bitcoin, right? Lightweight clients get in touch with a full node. So here also, and these full nodes are known as trampoline nodes. Basically, their only responsibility is to route the payment, take the payment from a lightweight node and route it further to the destination. All right. Now the issue here was that the last trampoline node, let's say one trampoline node takes it and gives it to another trampoline node, that gives it to another trampoline node, and that gives it to Bob. So the payment goes from Alice to Bob. Now the final trampoline node will get to know that the recipient is Bob. So Bob's identity will not be hidden. But now what happens is that in trampoline payments, you can use the concept of blinded paths. What is a blinded path? It is basically a concept where the recipient remains anonymous. Okay, so the recipient can just say that, hey, pass the payment to such and such node, and I'll collect it from them. Okay, so uh, if I had to give you an example, it's like when you order something from Amazon, you have two options. First is a door delivery, where Amazon will come to your house and deliver the product, right? Which is not anonymous. Then Amazon knows what your address is. Okay. The second option is they have these pickup centers in your area where you can go to the pickup center and pick it up. All right. So you can tell Amazon to deliver the product to the nearest pickup center in your locality. You can go to that pickup center and pick up the product. That way, Amazon does not get to know your address. Blinded path is very similar to that. If Alice wants to send a payment to Bob will not share his public key with Alice. Bob will just tell Alice that, hey, this is a node that is connected with me. You drop it to this node, and I will collect it from this node. So Alice will never get to know Bob's identity. Alice will just hand it over to the node which Bob has told Alice to hand over the payment to. And from there, that node will route the payment to Alice through unannounced nodes. All right. So basically, the sender does not know the identity of the recipient, and anybody in the public domain does not know the identity of the recipient. So blinded paths basically is a mechanism through which the recipient's identity is concealed. So what Eclair does is that for trampoline payments, it has enabled blinded paths so that lightweight clients can receive payments while remaining anonymous and not sharing their public key with anyone on the network. That's broadly what this update talks about. Then we have LND number 816, which allows an LND node to mutually close a channel that still has one or more pending payments. All right. So up till now, what was happening is that when you give a shutdown message, all right, when an LND node issues a shutdown message, immediately the channel was closed. Even if there are pending HTLCs, those pending HTLCs would not get executed. It's just like, for instance, you're using a computer and you remove the plug, and all of a sudden everything shuts. It does not wait for you to shut down smoothly. So that is what the mechanism was. The pending HTLCs would be aborted. But now there is this new update. What it does is that the pending HTLCs will first get executed, and when there are no more pending HTLCs, systematically the channel will be closed. LED number 7733 updates Watchtower support to enable backing up and enforcing current shutdown of the simple taproot channels that are now supported experimentally by LND. Taproot channels basically are lightning channels that enable you to send the funding transaction can be P2TR, and the commitment transaction will also be a P2TR. That's broadly what it is. All right. Your funding transaction can be P2TR, and your commitment transaction can also be a P2TR. So lightning channels that enable funding and commitment transactions in the form of P2TR are known as simple taproot channels. These are not implemented, they're just being considered. So LND updates Watchtower support to enable backing up and enforcing correct shutdown. So basically, they're working towards enabling simple taproot channels where lightning channels will have commitment and funding transactions as P2TR, and they have enabled backing up and enforcing current shutdown. So those channels will be backed up correctly, and the proper mechanism of shutdown, as mentioned above, will be implemented also for the taproot channels. We're at 9. We'll try and wind it up in 5 minutes if that is fine with everyone. All right. LND number 8275 begins requiring peers support certain universally deployed features as specified in modes. So you can go through the newsletter. I think it was Rusty Russell. Okay, the previous newsletters links have been given where Rusty Russell mentioned that there are certain features in Lightning, in Bolt, which are not used by any of the nodes anymore, so they should be abandoned. And there are certain features which almost every node uses, so they should be mandatorized. Those features that he talked about are variable size onion messages, toxic queries, data loss protection, and static remote party keys. So we can go through this article later on. Variants. Currently we have onion messages that can be only of a fixed length, and they can have only fixed hops. What variable size onion messages do is that they allow you to vary the size of each onion message, but the entire length should be the same by limiting the number of hops. What is gossip queries, data loss protection, static remote party keys? We can read through this because we're running out of time. So basically, yeah, these were some proposals that were made by Rusty Russell. They have been implemented. Rust Bitcoin. All right. So there was this method in Rust Bitcoin .txid such that when you give it a transaction object and you invoke this txid to it, it computes the txid of the transaction and gives it to you. All right. Now this is a very data intensive task, and that is why the nomenclature has been changed. Instead of txid, the name has been changed to .compute txid, so that it gives the notion to the programmer that, hey, this is a very data intensive method. It will require a lot of computation. So before invoking it, think about it. If you're not in need of it, don't invoke it. So my understanding is that the functioning of the method is the same. It's just the nomenclature that's been changed. The same for WTXID, which is witness transaction ID, and NTXID, which is non-witness transaction ID, because this is for SegWit transactions because they have a witness data which is separate from the entire transaction. So the nomenclature has been changed in Rust Bitcoin. I just deprecated the old one, TXID, and has been replaced by .compute TXID for non-SegWit transactions and WTXID and NTXID for SegWit transactions. HWI, that's Hardware Wallet Interface for Bitcoin Core, adds support for the Trezor Safe 3 hardware signing devices. We just covered this. The latest update for Bitcoin Core's hardware wallet interface has added support for Trezor 3, Trezor Safe 3. BDK 1172 adds a block by block API for wallet. So basically, they've added an API for each wallet, which will give that wallet access to a sequence of blocks such that the wallet can iterate over that blocks and update its data set. So, for instance, if a wallet is outdated, it feels that its data is not updated. Using this API, it can iterate over a sequence of blocks where it feels there are relevant transactions that it is not aware of and access that data and update its wallet information, its balance, etc. This is in BDK. The final one is bananas. What they've done is they've added bin 24-5 with a list of specification repositories related to Bitcoin such as BIPs, holes, blips, slips, LNBPs, and DLC specifications. Some specification repositories for other related projects are also listed. What's Banana? It's Bitcoin Inquisition names and number authorities, I think. So this is very interesting. I found it very interesting. I came across it for the first time. We just go through it. It is nothing but a Bitcoin repository, which is an integration or a collection of all the bips, all the blips, all the slips that you'd like to go through. All right. So, like for instance, if you wanna, they have collected all the Bitcoin bips and all the slips, Satoshi Labs Improvement Protocol, the bolts, right, basis of Lightning technology, the blips, Bitcoin Lightning Improvement Proposal, LNBP, DLC specs, Mint, Banana, all right. Now, what you can do is let's say you are interested in studying a specific BIP. It could be any BIP, BIP 119, whatever. So you just come to this repository, you click on BIP, you will get a list of all the BIPs that they have. All right, what is the motive behind that BIP? See, from BIP 1, BIP 2, all the BIPs are here. So you can click on any of those folders, read whatever's written, go through the code, go through the comments. Okay, everything has been included at one place. So whoever wants to study a specific BIP can just come on this repository and all the BIPs are here. Likewise, if you want to study a bolt, a specific bolt, what that bolt is doing, saying what code does it include, then you can click on this blip. Sorry, a bolt. If you want to see a Bitcoin Lightning Improvement Proposal, then you click on blip, and you'll find all the Bitcoin Lightning Improvement proposals there. And the latest one, if you see in 2024, they've included these ones: check sig from stack, op internal key. These are like a pass. These are a part of L-enhance protocol that we studied earlier. So every time there's a new Bitcoin improvement proposal, they will create a repository. They will add the relevant code to it, the documents to it, and everything. So whoever wants to study BIPs or blips or bolts, they can come to this repository and it gets updated regularly, and they can access all of this information like on one page, which I find very handy and useful. So we've come to an end of this week's newsletter. Any closing thoughts? Any
Yeah,
questions? Anything
bananas are
anybody would
really
like
cool.
to share?
I was saying bananas are really cool. I was not aware of something like this.
Exactly. Even I wasn't. I found it very amusing and interesting. And somebody's taking up so much time and effort for just integrate. I mean, it looks very trivial, but when information is scattered, it's very difficult for you to access. When somebody just integrates that scattered information to one place, it does wonders.
Yep, yep.
It looks pretty new though. Like the repository was started 3 weeks ago.
Let me see. Where did it go?
Banana.
How did you info that,
Click on banana.
Oh, I went to the commit history. Like there are just 13 commits. Like if you click 13 commits under the green code, if you click that and scroll down.
What's the date? Jan 30. That's the latest commit, right? Jan 30. Yeah, 3 weeks ago. Yeah, it's pretty new. I think they discussed it in the newsletter that we skipped. 285 we did, and I think they discussed it in detail in 286, which we skipped. And in 287, they are like sharing what's the progress. So maybe we missed it in the newsletter that we skipped.
Makes sense.
But I think this is great. Now we are up to date in terms of newsletter. So we are discussing the things which are which have just gone live.
Right. But I mean, ironically, this week they've not posted the podcast on their website. The podcast happened. I listened to it on Twitter. They have it on their Twitter timeline, but they have not uploaded it on their website. I don't know what's the reason.
Yeah,
It's
I
the
also
first time
didn't
I've
see
never
it.
seen this.
Yep, I also didn't see it.
Yeah, they've not posted it. But yeah. Anyhow, all right. So we'll wind up for the day, guys, or for the night. Yep, Saurabh.
Yeah, no questions from my side. Great job as usual,
Thanks
Faisal.
for hosting.
Yeah, thanks for hosting.
Thanks a lot for showing up, everyone. All right. So yeah, good night. Enjoy your lunch,
And hope to
and
see all of
we'll
you
see
on
you next time.
Wednesday.
Bye. Sorry.
I'm saying hope to see all of you on Wednesday for our first session of How to Think About Economy.
Yes. And also hope to see you tomorrow, Saurabh. What is tomorrow?
Mastering lightning. Yeah, I'll try to
Yeah.
come half an hour late as
Okay.
usual.
All right.
All right,
Fine. Okay.
take care.
Bye. Take care.
Bye, everyone.
Thank you, Faisal. Good night, guys.
Okay.